Now we're going to use the Newton-Raphson method again, but in context. So the value of a car can be modeled by the formula V equals 20,000 times 0.85 to the power of x minus 100x, where x is the number of years since the car was purchased. Show that the value of the car is 0 in the interval 15 to 16. So if we substitute in 15 and substitute 16, we should show that it goes through 0 between 15 and 16. So when x is 15, we should get a positive. So V is 20,000 times 0.85 to the power of 15 minus 100 times 15. And we get £247. And then when x is 16, V should become negative. Negative £115. So there's been a change of sign. Therefore, it's gone through 0 between 15 and 16 years. Using x0 as 15.5, the first approximation, use a Newton-Raphson method to obtain approximation for the time when the car's value is 0. So we've got 15.5 as our first approximation. We need to put 15.5 into the function. So that would be our f of xn. And we haven't worked that one out. So when x is 15.5, what's v? $60.7. So v is 60.7. So that is our f of x, 60.7. f of x 0 is 60.7. We also need the gradient function. So we're going to have to differentiate our v to get dv dx. dv dx. So when we differentiate something to the power of x, something in the form ax, y is ax, dy dx is ax ln a, ax times log a. So we have dv dx is 20,000 times something in the form a to the power of x. So we're going to have 20,000 still times the a to the power of x still, but times log a. And our a was 0.85, so log 0.85. And 100x is going to differentiate to give 100. So that's our gradient function. And when x is 15.5, our gradient is 20,000 times 0.85 to the power of 15.5 times log 0.85 minus 100. And that's negative 361.8. So now we've got all the information we need to put into our Newton-Raphson. So the next approximation is the first approximation. So x1 is x0, which is 15.5. Take away f of x0, which was our 60.7, over our gradient at that point, which we've got negative 361.7. Or was it 0.8? 0.8. So let's just type this into the calculator. So we could have this one stored as A, and this one stored as B. So if we have 15.5 minus B over A, we get 15.7. So our second approximation is 15.7 years. One question for you to try. See if you can give it a go. So we have to be careful because we're looking for a maximum height, not a point where our function is equal to 0. So because we're looking for a maximum height, that is where the gradient is 0, not where the function equals 0. So we're going to have to differentiate, and probably the best thing to do is use the product rule. So u is, with more space, u is 4x minus x squared. V is e to the power of x. So du dx is 4 minus 2x, and dv dx is e to the power of x. So dy dx, or dh dx, as the case may be, dh dx is e to the power of x times 4 minus 2x plus e to the power of x times 4x minus x squared. We want to show that there's a maximum in the interval 3 to 3.5. It might be nicer actually if we factorized out the e to the power of x, which will leave us with 4 minus 2x plus 4x minus x squared, which is e to the power of x times 4 plus 2x minus x squared. So, show that there's a maximum in the interval. Let's do substitute in 3. So when x is 3, our dh dx is e to the power of 3 times 4 plus 2 3's minus 3 squared, which is 20.1. We're using that later, so I'm going to store that as A now. And when we have 3.5, we get negative 40.4. $41.4. So we have a change of sign. So if we were in an exam, we'd write change of sign, continuous function, therefore maximum is in the interval 3 to 3.5. But we can just see here, we've got the change of sign. And now we're going to use the Newton-Raphson method. So we're actually going to have to differentiate again. The function we're using is this function. This is the one we want to know where it's equal to 0. So this is the function we're using. So we're going to have to differentiate it again. So we'll have u as e to the power of x v as 4 plus 2x minus x squared. So du dx is e to the power of x. dv dx is 2 minus 2x. So our gradient function, what we're going to be using as our gradient function is e to the power of x times 4 plus 2x minus x squared plus e to the power of x times 2 minus 2x. So we are going to be substituting our 3 into this gradient function. So substitute 3 into here. So we'll get e to the power of 3 times 4 plus 2 3's minus 3 squared plus e to the power of 3. We could have made this simpler by factorizing out the e's times 2 minus 2 3's. And we get negative 60.3. Negative 60.3. So now we've got everything we need for our Newton-Raphson. So x1, our second approximation, is our first approximation, which was 3. Take away f of 3, which we know, and that was our 20.1, over 3 into our gradient, which was negative 60.3. So it was 3 minus the one we saved as a over our last answer, and we get exactly 10 thirds, 3.3 recurring.